Deep within the arid bedrock of the Arabian Peninsula lies a geological structure where water is produced under conditions that diverge from standard aquifer models. Directly above the Wadi Ibrahim aquifer, millions interact with a localized water source in one of the most densely populated seasonal catchments on Earth. The well shaft descends 30.5 meters, cutting through 13.5 meters of sandy alluvium before boring 17 meters into the underlying diorite bedrock. This shaft provides the historical interface point where humans have accessed this subterranean system for centuries. In most shallow desert wells, high urban density and physical depth constraints lead to rapid degradation and fluctuating chemistry. This specific source, however, maintains a consistent mineral profile that does not fail under these pressures. Establishing an analytical framework requires looking at the 2012 Schomar assays from the University of Heidelberg, which mapped the trace elements using mass spectrometry. These assays show a total dissolved solids count of 2,000 milligrams per liter, while standard commercial bottled waters range between 150 and 350. Shallow desert aquifers typically fluctuate as rainfall dilutes minerals or drought concentrates them. Here, the 2,000 milligram count remains remarkably stable. This stability raises a specific question. How do these chemical markers persist without degrading or diluting in such a high-demand environment? The data reveals a geochemically stable anomaly, a high-concentration mineral solution maintained by the unique pressure of the Wadi Ibrahim system. Researchers process the water using inductively coupled plasma mass spectrometry to identify the exact mineral concentrations that define this source. The spectrograph shows an alkaline pH of 8.0 with bicarbonates at 366 milligrams, calcium at 95, and potassium at 50. When mapped against standard European spring profiles, the Wadi Ibrahim data occupies an expansive footprint, far exceeding the mineral density found in alpine sources. The alkalinity of the water facilitates this density. A pH of 8.0 interacts with the trace metals to ensure they remain perfectly soluble and integrated into the solution. This high mineral load provides a heavy chemical buffer, allowing the water to resist environmental changes that would typically lead to standard degradation. Trace element analysis isolates a lithium concentration of 15 micrograms per liter. Most commercial bottled aquifers register near zero. While lithium is often noted for its physiological role in neural stabilization, its consistent presence in a shallow well like this is geologically rare. To find the source of these elements, we look to strontium isotopic mapping, which acts as a definitive geological fingerprint for tracking water origins. This plot shows that while surface runoff clusters in a shallow quadrant, the Wadi Ibrahim sample sits in an isolated zone. This indicates a deep crustal origin, where the water interacts with rock at depths far below the well shaft itself. These elemental ratios suggest the water interacts with the host rock at pressures and depths that are not found in standard shallow well models. Standard filtration typically occurs as water trickles through porous limestone or volcanic rock, which passively cleans the water before it reaches the aquifer. The Wadi Ibrahim aquifer uses a different matrix, where sandy alluvium meets dense diorite and basaltic bedrock. This split screen shows standard limestone on the left and the diorite interface on the right. A half-meter layer of weathered rock sits between sand and bedrock. As water moves through, the high-pressure interface strips minerals and trace metals directly from the diorite matrix. The aquifer's stratigraphy facilitates active mineral leaching, where high-pressure flow forces a rapid chemical exchange between the water and the diorite bedrock. This chemistry also addresses a biological challenge. Shallow wells in urban catchments typically accumulate E. coli, or algae without synthetic chlorination. Analysis of the Wadi Ibrahim water shows elevated natural fluoride concentrations integrated into the pH 8.0 baseline. This alkalinity, combined with the presence of fluoride, creates an environment that prevents the growth of pathogens. Microbial cells cannot survive or divide in these specific conditions. This interaction produces a sterile biological profile naturally, maintaining water quality without human intervention or chemical additives. The geological properties of the well maintain a biological profile that remains sterile through the natural interaction of high pH alkalinity and fluoride ions. The final factor is the sheer volume of water produced by this location. Historical yields during peak demand have reached 10,000 cubic meters per hour. Maintaining this volume in the hyper-arid Arabian Peninsula requires a recharge rate far exceeding what surface rainfall alone can provide. This relentless recharge indicates a deep crustal pressure system is driving the flow, moving water independently of local rainfall patterns. The data reveals a specific hydrogeological profile, a deep crustal strontium signature, a consistent 15 microgram per liter lithium concentration, and total biological sterility. While most global aquifers are filtered for low mineral purity, the Wadi Ibrahim system is geologically configured for high-density mineral delivery.